All right, so here we've got the notes for section 2.6, the graphs of rational function, sorry. So just the definition first, let f and g be polynomials with g of x not 0, because it can't be 0, otherwise we're trying to divide. Then the function given by r of x equals f of x over g of x is a rational function. So example 1 down here says find the domain of f and use limits to describe the behavior of the values of x not in its domain. So since we have a fraction, we can't divide by 0. So if you want to find the domain of a rational, you set the denominator not equal 0 and you solve. So the domain for this function is all values except for 2, which means that we have actually a vertical asymptote there at positive 2. If we look at the graph, so there's 2. If x is more than 2, I'll be lazy. What is it? 1 over, oops, I'm going to delete this guy too. 1 over quantity, wrong quantity, x minus 2. Draw. Here, there we go. So we've got a vertical asymptote right there, and the graph does something like this. So use limits to describe its behavior at values of x not in its domain. So the limit as x approaches 2 from the left of our function is equal to negative infinity, because as we come from the left, we go down. This chunk over here, the limit, as we approach 2 from the right of our function, goes to positive infinity, so it goes up. Okay, transformations. One of the simplest rational functions is the reciprocal function, 1 over x. That can be used to generate many of the other rationals. The graph of any non-zero rational function of the form ax plus b over cx plus d, where c not 0, because then you don't actually have a rational because there's no x in the denominator, can be obtained through transformations of the graph of the reciprocal function. If the degree of the numerator, the top, is greater than or equal to the degree of the denominator, bottom, we can use division to rewrite the rational. So, example 2. Describe how the graph of the given function can be obtained by transforming the graph of the reciprocal function. Identify the horizontal and vertical asymptotes, use limits to describe the corresponding behavior, sketch the graph of the function. So this up here is going to be a vertical stretch by 2. This plus 3 on the bottom is going to move it left 3. For a rational, you generally have things that look like this. Bx plus c plus d. So in this case, A is a vertical stretch, B will control horizontal stretches, compressions, C will move the graph left or right, and D moves the graph up or down. So that's why we didn't have anything else. So the reciprocal function by default is centered at 0, 0, and goes through 1, 1, and 1, 1, or 1, 1, and negative 1, negative 1. But if I move everybody vertical stretch by 2, that means it's going to go over 1 and up. 2, negative 1 to negative 2. So it's going to be more taller. It also goes left 3 units. So every point here is going to go 1, 2, 3. It's going to be over here. So instead of the axes, instead of being centered at 0, 0, it's going to be centered at negative 3, comma, 0. So the graph does something more like this, like that. So identify the horizontal and vertical asymptotes. So we have a vertical asymptote at x equals negative 3, because that makes the denominator 0. We have a horizontal asymptote at y equals 0, because the graph flattens out as it goes to 0. Limits to describe the corresponding behavior. Okay, so the limit, we'll do our verticals first. As x approaches negative 3 from the left of our function, goes down. Limit x approaches negative 3 from the right, goes to positive infinity. The limit, so horizontal asymptotes are as x goes to infinity. Now we'll be lazy. Plus minus infinity becomes 0. Okay, so down here, so this one we need to do some actual division first. We need to work out what 3x minus 7 divided by x minus 2 is. So I'm actually going to use synthetic. So 2 is the 0 of that, 3 and negative 7. So 3 falls down, that's 2 times 3 is 6. That drops down. That is -1. So if you have a remainder with synthetic, since this originally was x, this has nothing. So this is 3 plus -1 over x minus 2. So this graph is going to go right 2, up 3, be flipped because of the -1. So essentially, instead of being...
This is Bradshaw. Please call extension 3069.
So essentially, instead of being centered at 0, 0, this graph is going to be centered at +2, 1, 2, 3, +3 right here. So we'll draw in some imaginary. So our center is actually up here. So since it's upside down, we'll actually do something like this. So this one has a vertical asymptote at 2, has a horizontal asymptote at y equals 3, where that is there. I'm not going to really work the limits. So as you approach -2 from the left, goes to +infinity, -2 from the right goes to -infinity. So those are we'll do these. So limit x approaches 2 from the left. So 2 from the left goes to +infinity. The limit as x approaches 2 from the right goes to -infinity. So there's my vertical asymptotes. My horizontal asymptote, the limit as x approaches positive or -infinity is equal to 3. Okay. So limits and asymptotes. So it says find the horizontal and vertical asymptotes of this function. Use the limits to describe the corresponding behavior of f. So our equation is x squared plus 2 over x squared plus 1. So to find the asymptotes, you can either look at the graph. So let me pull the graph up here real fast. So x squared plus 2 over x squared plus 1, looks something like this. So, lovely little shape there. So to find the horizontal asymptotes, what you actually do is you use, actually it's going to come up down here, but what's referred to as the end behavior. So you actually just look at the lead terms. So I'm going to only worry about these guys. So x squared over x squared. That reduces to 1. So what I want to do is I want to take the limit as x approaches positive negative infinity of 1. Well, since there's no place to plug into, that's just 1. So that's my horizontal asymptote at y equals 1. To find the vertical asymptotes, I look at just the denominator, and I set it equal to 0. Because that's what causes vertical asymptote. So this becomes x squared equals -1. So x is equal to plus or minus I, which isn't a real number. So this graph has no vertical asymptotes. And if you look at the graph, there aren't any. There are no spikes. If you look at the graph as it's running left and right, it is leveling out at y equals 1. So down here, it says graph of rational has the following characteristics. The end behavior. So if n is less than m, meaning the degree of the numerator is less than the degree of the denominator, the end behavior is 0. If they're equal to each other, the end behavior is the horizontal asymptote, lead coefficient on top divided by lead coefficient on bottom. So in this case, this was what I had here. They're both 2, so it's 1 over 1 or just 1. If n is more than m, so numerator larger than denominator, the end behavior is the quotient polynomial function q of x, where you actually have to work the division out. So there is no horizontal asymptote if the numerator has the larger thing. The end behavior talks about what the graph does. Vertical asymptotes, these occur at the real zeros of the denominator, so that's actually what I did up here. So I set the denominator equal to 0, solved, but it's the real zeros, so these are not real. Provided the zeros are also not zeros of the numerator of equal or greater multiplicity. So if they also are a 0 of the numerator, they don't count. X-intercepts, these occur real zeros of the numerator. So if I set the numerator equal to 0 and solve, that'll tell me where it crosses the x-axis. The y-intercept, this is where you plug 0 in for x and get an answer. So our graph would cross at 2, because if I plugged 0 in for x on top and bottom, this becomes 0 plus 2 over 0 plus 1, which is just 2. Okay, so turning the page over. Whoops, hit the camera. So it says if the end behavior asymptote of a rational function is an oblique or slant line, we call it an oblique asymptote. An oblique asymptote is also sometimes called a slant asymptote. Find the asymptotes and intercepts of the function, blah, 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 and graph the function. So, to find the asymptotes, so our equation is x cubed over x squared minus 9. So I need to actually work this division out. Oh, that's a lie. No, it's not. But I can't use synthetic because that's not an x. So x squared minus 9 is going to go into x cubed. I'm actually going to fill in all of the values less than it, just so I have a place to put it. So this is going to be x, so x times x squared is x cubed, x times negative 9 is negative 9x, and then I subtract all of this stuff. So those go away. I have 0x squared comes down, I have positive 9x, and then the last 0 comes down. So then this is going to be plus 0. 0 times x squared is, so 0x squared, so that actually goes away. So that's my remainder, 9x. So this division is x plus 9x over x squared, what is it, minus 9. So if you actually look back at the previous page, I talked about the end behavior. So if n is more than m, which is what we have here, the end behavior asymptote is the quotient polynomial function q of x. So what we get when we do divide, so it does not matter about the remainder. So this one does have a slant asymptote. The slant asymptote here is y equals x. And if I graph this guy, so x cubed on top over x squared minus 9, and we'll graph the line y equals x. See if I can get it to show up. There we go. So there is my graph. So there's y equals x, and then the curvy stuff is actually the x cubed over x squared minus 9. So as you notice that the curve, let's see if we can turn it off here. Select. There we go. Okay. So there's just the x cubed over x squared plus 9. Or minus 9, whatever it was. Minus 9. So and if so you notice these graphs do keep going up forever, so there's no horizontal asymptote. But it does approach what I get if I actually do the division, y equals x. So that's my asymptote. The intercepts of the function, so to find the x-intercept, I need to solve the numerator. So I'll do that over here. So the x-intercept, I set x cubed equal to 0 and solve. Well, that's 0, so there's only one x-intercept. To find the y-intercept, I plug 0 in for x, so 0 cubed over 0 squared minus 9. Well, that's 0 over negative 9, which is 0. If you look at the graph, it crosses the origin at 0, 0. So intercepts and graph the function, which we did. So real roughly, it does something like this. And then remember, that was our y equals x imaginary asymptote line. All right, example 5. Intercepts, asymptotes, use limits, blah, blah, blah. Vertical asymptotes, draw the graph of the rational function, this guy. So if I want to find the x-intercepts, I set this numerator equal to 0. So this will have an x-intercept at 1. To find the y-intercepts, I plug 0 in for all the x's, so I'm going to be lazy. It's going to give me negative 1 over negative 6. So that's 1/6. So intercepts. So for the asymptotes, so in this case, this numerator, the degree of the numerator is less than the degree of the denominator. So I'm going to have an asymptote at y equals 0, because that was from the previous page. And to find the vertical asymptotes, so this is actually the horizontal asymptote. To find the vertical asymptotes, I need to set the denominator equal to 0. So we'll do that over here. So x squared minus x minus 6, this is factorable. That's x minus 3, x plus 2. You can do the quadratic if you want. So I have a horizontal asymptote, sorry, a vertical asymptote at x equals 3, because that makes that 0, and over the quantity x squared minus x minus 6. So we'll hit the initial view window. So graph looks like that guy. So I'm just going to talk, I'm not going to write them out. So as you approach -2 from the left, you get negative infinity. As you approach -2 from the right, you get positive infinity. As you approach 3 from the left, you get negative infinity. As you approach 3 from the right, you get positive infinity. And the limit as x approaches positive or negative infinity is 0. The graph flattens out. And draw the graph. Okay, so it looks like this. So we have 1, 2, 3, 1, 2. So we have a vertical asymptote here and one here. And we're going to go cross through. X-intercept is at 1. So it does something like that, which is roughly that guy. All right, so 6, find the intercepts, analyze, blah, blah, blah. So the intercepts, so to do the x-intercept, we set the numerator equal to 0. So 2x squared is equal to 2, x squared is equal to 1, so x is equal to positive or negative 1. Because remember, when you take the square root, you get 2 solutions. For the y-intercept, we plug 0 in for all the x's, which gives me just -2 over -4, which is positive 1/2. And then we'll sketch the graph here. So this one's going to have a horizontal asymptote at 2, because these have the same degree. So we'll just count up to here. So I know there's going to be some horizontal line there it won't cross. Let's look at the graph on my calculator then. So quantity 2x squared minus 2 over x squared minus 4. Draw. So it looks like this. We'll zoom out just a little bit. There we go. That's a little bit better. If you notice where the spikes are, that's because if we look at the denominator, if we set the denominator equal to 0 and get the vertical asymptotes, this becomes x squared equals 4. When I take the square root, I get x. Sorry, these are not equals to get the vertical asymptotes, plus or minus 2. So there's also some imaginary lines here at positive 2 and negative 2 that my graph will not cross. So it has to go through -1 up to 1/2, because that's the y-intercept, and back down through -1, and then so there's the shape of my graph. Okay, example 7, find the end behavior asymptote of this guy and graph it together with f in 2 windows when showing the details around the vertical asymptote. And well, we're not going to do the graphy part. So end behavior asymptote, that's where you just take the lead terms. So the end behavior asymptote for this guy is just x squared. What that means is, let's actually do some of the graph. We'll look at the graph. Minus 3x squared plus 3x plus 1 over x minus 1. Draw. So there's my graph. What happens is, if I zoom out a lot, the shape of that graph, it's kind of harder to tell, starts to look more and more like a parabola, because the end behavior model is just y equals x squared, which is a basic parabola. So that's saying as I get farther and farther away from the center, my graph eventually will just look like x squared. That's what end behavior is. Okay, and I believe that brings us to the last example, number 8. Find the intercepts, analyze, and draw the graph of the rational function. Can we just do that? X cubed minus 3x squared plus 3x plus 1. Oh, okay. So intercepts. So the x-intercept occurs where the numerator is equal to 0. So x cubed minus 3x squared plus 3x plus 1. However, I don't particularly want to algebra this, so I'm going to let calculator man handle it. So gsolve root. The x-intercept occurs at negative 0.26-ish. I believe that is the only one. Okay, the y-intercept occurs when x is 0, which leaves in the numerator just 1, on the denominator just -1, so the y-intercept occurs at -1. So to do the sketch, I'm going to cross about here, there, so there's a piece that does like that, and there's another piece. So we have a vertical asymptote at 1, because if you look at the denominator, it can be 1 there. So then it does something like that. So there's my graph, which brings us to the end of this section.